Okay, Assalamu alaikum, Shabam. I hope you had an enjoyable weekend. I'm still not yet finished with your quiz. It shouldn't take this much from me, but I have to admit that I have some other hard things to finish and I cannot give it the proper attention it deserves. So you need to be patient a little bit. But inshallah, soon you will get the grades. Today, ya Shabab, we are going to continue working on the shear stress due to bending. And before I move on, I would like to give you an important hint. Last week, I wasn't consistent when I was taking the attendance, not necessarily after 10 minutes from the beginning of the class. And I realized that some students were giving me the comments that, oh, we thought you will only do it after 10 minutes. And so I don't know, ya Shabab, how far you can secure your own private place during the class. But I mentioned this in the beginning, and I told you that we are definitely going to ask you to turn on the webcam during exams. I didn't do it in the first quiz. I am pretty much confident I will do it in the second quiz. One reason for this, I don't want to overwhelm you by, experiencing the first quiz, the first time you upload picture. As you have seen, there were students who had struggled with uploading their quiz, and they ended up sending it to me by email, which is totally not nice. So I thought, let's me attack it one by one. But what you should know is while the quiz is 15 minutes, while the attendance is 10, maybe 3 minutes, the exam is going to be longer and you will have to switch on your webcam. So my only hope is that there is no issue. Okay? I understand that some of you may not have enough space to claim for many hours in the day. And I am very sorry if this is the case, but I have no other choice. So please try to work on this. Okay, so can you see my slide, ya Juan?
Yes.
Okay, so
yes.
Last time, ya Shabab, what did we talk about is the shear stress due to bending. And for example, if we look at this scenario, this is a beam which is fixed at the end, and there is an applied force of P at the end of the beam. Now we know if we draw the reactions, that's going to be a minus P and a reversed moment. Now, if I draw the shear force diagram, it will be equal to the force over here. It will continue the same until the end. This one will take it down to 0. And if I draw the bending moment diagram, it will be like this. That's what's going to happen. So the conclusion, if you recall, is that at any given moment, whenever you have a bending moment, you will have a shear force. Now, this shear force is represented here. As you see, it's acting along the surface and inside the material. And that's why we have the cracking happening in this way, because of that shear going in. Do you understand? So this is in a case very important. And think about it, ya Shabab. You may not feel it as very important, if you have a block of steel, you cannot imagine that a block of steel will just have a crack like that, just like the wood. But remember, you can have structure, for example, which are glued together. Yes, you can glue to an I-beam together, and in this position where the shear, this shear is going to act along the glue surface, it might cut the glue for you. So this is very important, and we must take care of it. Now, if you do not remember, this class will be all about trying to remind you about how do we deal with the shear force in bending. Now, the equation, I am pretty sure it is not very strange to you. It is this, it's a shear stress, which is equal to V, the shear force, multiplied by Q. Q is the first moment of area, divided by I. I is the moment of inertia, and P and B is the thickness. Okay. Now, I hope that during the discussion you will keep remembering things from CE203. Now, let me give you an example, and I have to warn you that this example may not be absolutely accurate one, but it has the feel of what does it mean to have a shear force due to bending. Okay. Now, if you have a rectangular beam like this, and I tell you, imagine that I'm asking you to have a knife, and then you put the knife here, and then you start cutting. Call this a knife or saw, minshar, it doesn't matter. And you start to slice, cut through the surface. Now, apparently, the feeling, the exhaustion that you will experience while you are trying to cut this bulky material will be different if you have a cross-section which is like this. And I ask you to cut here. Isn't that true? Isn't that true?
Yes, it's true.
Yes, true.
So the reason is this: while you are cutting, this space is empty, and you are actually cutting this and this. That's B. B is what you feel when you cut. So let's just imagine that you are a freelancer, somebody who does, labor work, and then you went to your client and he asked you, cut this beam from here. Okay, you take the saw and you start cutting. And after you finish, he tell you, well, you want your money, right? I am gonna give you your money, but now I need to, ask you to cut it right here. And then, without you even noticing, you will understand automatically that when you cut, you will actually, ya shabab, if you think about the cross-section like this, you will actually position the saw here and here. But let's assume that your client is a very tough guy. يعني باللهجة العامية نذل. وجاء وقال لك no. I don't want you to cut it this way. I want you to cut it here. وطبعا انت حتتناقش وياه وتقول له وش تفرق وليش وش ذا الحالة هذه، فما في فايدة، ما راح يعطيك الدراهم. Now it's totally different. You will be super exhausted because you have to, you have to cut all of this thick part. And this is why P will be different. In here, B is all of this. In here, B is the little one. Now, the difference even in the feeling can be expressed mathematically using this relation. So indeed, ya akhwan, what will happen is that shear stress, the distribution of this thing is changing. The value of tau is changing. We just told you. You cut it one place, you don't feel tired. You cut it another place, you feel tired. You don't feel tired, and so on. So if you recall, when they told you in CE that the distribution tau is going to be like this, and it is very funny if this client try to play you, okay? جاء الكلاينت هذا من الاشخاص يا شباب اللي يحب الالغاز عدل وقال لك ابغاك تقص هذا بس فوق الخط هذا، فتقوم انت تقول له يعني كيف؟ يقول لك ايه قص الهواء. فطبعا انت تعرف انه هو قاعد يستعبط عليك، لكن he is your client، يعني من you have to give him what he wants, otherwise he will not give you the money. So maybe you will be like a fool who is trying to just saw himself moving the saw in the air, trying to cut the air for the guy. How much is the tau? How much, ya shabab? When you cut the air? Yeah, it's almost zero. It's nothing. So this is why tau here, right there, at the end, when there is no B, just at the end is 0. But right there, it is maximum. Now, this is the part when my example break down. It is no longer correct. In reality, if you cut here and here and here and here, you will spend almost the same effort. It doesn't matter. But with respect to the equation, it tells you that there is something else with shear, not the cutting. انتهينا يا شباب من المثال. المثال هنا يخرب. Okay? In mathematics, in reality, that shear will increase and it will reach the maximum somewhere. This somewhere is actually the neutral axis, where the bending moment goes to 0. So we need to be very careful. We need to know when should we use this and where. If we are designer and we are always looking at the worst scenario, worst case, we might be looking for tau when it reaches maximum. And if, for example, the geometry has a feature like a hole or something, which make me ask the question, what is the shear here? Then I should use this equation and substitute the number such that I know the shear in this position, although it is not maximum. Good. Now, I over here is the moment of inertia of the cross-section. I تحسبها مرة ما لها شغل هل أنت قاعد تحسب الشير ستريس هنا أو هنا أو هنا أو هنا. It doesn't matter. I is a property of the cross-section. So you would know V, you would know I, you need to think about B. B is a little bit tricky. And you need to know how to calculate Q. Now, I'm pretty sure you forgot how to calculate Q, but Q, if for a rectangle, is simple as B over 2C square minus Y1 square. You probably ask what is C, what is Y1, I will show it to you. So if you have a rectangle, then this is the neutral axis. The maximum distance to the end is C, and Y is any distance in between. Of course, Y, when it reaches to C1, to C, they will cancel each other out, and that's how you get 0. Q will become 0. Okay? And now if you look over here, there is very interesting equation. This value represent the maximum, this magnitude represent the maximum value that tau can reach to, which is represented by tau max. Now let me write this equation in a big word for you. Tau max equal to 3v over 2a. Now I want to ask you a question. Tau equals to vq over ib, and tau maximum equals to 3v over 2a. What is the difference يا شباب؟ متى تستخدم هذه؟ متى تستخدم هذه؟ بالحظ، بالنصيب؟ How?
The maximum is for the rectangular cross-sectional areas. And if we change the cross-section, we can use the general one, which is the one at the top. But if we derive the first one, we can get the second one in case we are working on a rectangular cross-sectional area and want to find the maximum value.
You need to be very careful, Faris, because the right answer, you almost got like 80% of the right answer. This equation is the general one. It is applied for all cross sections. If you apply this equation for a rectangular cross section exactly in the middle, not anywhere, you will get this. So indeed, this equation is general for any point in the cross section. This one is an equation which gonna give you the stress at only one little section, which is the middle one only. هذه مرة specific. هذه ما تطلع لك shear stress for rectangular geometry. هذه تطلع لك الماكسيموم shear stress in a rectangular geometry. It's not any stress. It's only the maximum. Is it this one? No. Is it this one? No. Is it this one? No, 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 no. It is only this one. Only. Now, if you look carefully, and as I'm going to show you in the example, V, ya shabab, is not difficult to obtain. V is not difficult to obtain. You will see from the shear force diagram. I, whether it is a rectangle, a circular, it is an equation given to you. 1 over 12 B H cube, whatever. B is always from the geometry. You need to think about it. There is no square, no cube, no square root, nothing. You just need to say, should I take this thickness or that thickness? That's it. However, Q is a lot of work. So you need to be very, very careful. Exam, ya shabab, is going to be open book. And by the way, even if you are here on campus, okay, we are still going to give you the textbook. The machine design, ya shabab, is an open book course. And these equations, you don't need even to memorize them. The problem is when students get confused. So let me show you. This table is very, very important. Why? Because it has the maximum value, the equation for the maximum value, okay, for very common geometries. Hollow, solid, circular, rectangle, and IB. These one are the maximum. So this is located here, this is located here, this is located here, this is located here. In the exam, or even a project, or a quiz, what does student do? Well, the student go and think that I should use tau equals to VQ over IT. And as I'm going to show you in the example next, you will spend some good time, maybe up to 15 to 20 minutes solving this problem, depending on the complexity of the geometry. بينما يا أخوان ممكن الجواب هو بالمعادلة هذه، بالله عليكم 3 على 2 رقمين V حتطلعه من الشير فورس دياجرام والاريا، يعني شنو الاريا؟ يعني الطول في العرض. And you will get the same answer. This is 3 minutes. This is 20 minutes. Now, what is the other mistake? Is to assume بأن المعادلة هذه does not exist and there is only this equation, this one. Well, this is also wrong, because maybe we will ask you to find the shear force in a location where there is no, it's not maximum. And we will see this in the exam. That's why, ya shabab, be careful, be careful. You need to know what are you doing. Can you shortcut your calculation by using this equation, or should you go and use this one? For now, ya shabab, I'm gonna stop sharing this, and I will turn on my computer screen, and I want you to start turning on your webcams. So. Is it screen? Can you see, ya shabab, the screen?
Yes, we can.
Yes.
Yes, sir.
Okay, let's get this over with. Hussein? بالراحة. Hussein?
Yes.
Okay. Where are you? Yeah, I can see you. صالح السعيد?
Yes.
عدنان؟
Yes.
Okay, محمد المدن؟
Yes.
Okay, صالح؟
Yes, doctor.
Okay. طويلب؟ علي؟
Yes.
Okay. وليد؟
Yes.
العمري؟ Okay.
Yes.
فيصل؟ Faisal, what is going on? Where are you, Faisal? Ali?
Yes, doctor.
Yeah. Muhammad?
Yes, doctor.
Bous, Muflih?
Yes.
Yes. Fahad?
Yes.
And Faisal?
Yes, doctor.
Muslih?
Yes, doctor.
Okay. Salman?
Yes.
Where are you, Salman? Okay, I can see you. Faris?
Yes.
Jibrin?
Yes.
فارس حامد
حمد.
حمد.
Yes.
طيب خالد.
Yes, doctor. Yes.
Yes. سعد. سعد. عمر.
Yes, doctor.
Umar, where are you? Yeah, I can see you. Ali, Mi'raj.
Yes, doctor.
Samir.
Yes, doctor.
Mustafa. Nuwaisir.
Yes, doctor. Here.
Okay. فواز العوفي. Yeah. أمجد.
Yes.
أمجد. Okay. فيصل.
Yes, doctor.
Okay. محمد.
Yes, doctor.
I still can't see you, يا محمد.
I see the cam, doctor. It's available.
Nasser?
Yes, Doctor.
Abdul Rahman?
Yes, Doctor.
Ammar?
Yes.
Umar?
موجود.
محمد؟
Yes.
مؤيد؟
Yes, Doctor.
محمد?
Yes, Doctor.
Okay. Anybody else?
Yeah, me, Doctor. Faisal Atoi.
Faisal, where are you?
And the bathroom, Doctor.
Anybody else? Okay. Okay, so let's go to an example, which I hope you can see my screen right now.
Yes, we can.
Yes? Okay, good. Now, what you see here is a beam which has been subjected to two equal loads, which are 40 and 40 kilonewton. Okay, these loads are, applied symmetrically with respect to the cross section. As you see, this is 0.4, this is 0.4, so the remaining ligament is 0.3, and as you see, we have a cross section which has a thickness of 12 millimeter and a height and a width of 100 millimeter. What do we want is to find the shear stress at point A. Look at point A. Now, in the solution, voluntarily, I am going to calculate the shear stress here. And then, if we got the time, we will ask you to go and check it. I will find the tau using VQ over IT, and then we will ask you to check if you get the same answer, which is 3V over 2A, which you should exactly. Okay, then we will talk about point A. So let's move on. Okay, the first thing is, let me go back over here and try to show you something. I mean, the reaction forces, if we call them RA and RB, and because the whole thing is symmetric, then RA is supposed to be equals to RB. And for that, if you sum up the forces along Y and you use up as positive, and you say this is equals to 0, you will have RA plus RA, which is RB, because they are the same, equal to 40 plus 40, which is 80. So you will end up with 2RA equals to 80, and this is going to give you RA equals to 40 kilonewton, which makes a lot of sense. You have two loads, two reactions, symmetry, 40 and 40. Each reaction will take one of these two forces. That's it. Now, if we draw the shear force diagram, it will become like this. It will go 40 at the reaction, because the reaction is acting upward. And then there is an applied force, which is 40, so it will go to 0. In between, there will be nothing, and then there is another force, which is minus 40, and then the reaction is 40, you go back to 0. So this is minus 40. Now, anywhere you pick, it doesn't matter. You have the same value, except إن واحدة منها negative, واحدة منها positive. So we will decide that V that we are going to use in the equation is 40 kilonewton. If you have any other way, different distribution, you would probably go for the location where V is bigger, maximum, okay? Now, if we want to find the shear stress in the middle, this is the middle of the cross-section. Now, what are we gonna do? We will split the cross-section into three areas. This is one, and this is another one. I am pretty sure you remember this, okay? But as I move on, you will remember it more. Now, what are we going to do? We will call this one A1, and these two, we will call them A2, okay? The distance, just to remind you, from here to there is going to be 50, right? The thicknesses are all 12, 12. Get that? Now, in order, before we move on, let's find I. I is not difficult because I is going to be 1/12 multiplied by 100 multiplied by 100 cube minus 1/12, 76 multiplied by 76 cube. How did I do this? Very simple. The big rectangle has 100 by 100, which is a square. So this is the first area. And its centroid is at the middle. And then I have another one, which is here. Now, this one has an area inside like this, and a centroid which is also on top of the other centroid. If the two centroid of the two areas are coincident, we can subtract them. Now, what is this dimension? This is 100 minus 12 minus 12. What is this? This is 100 minus 12 minus 12, which is 76. You got that, ya shabab? So if you have any question, you stop me, okay? This is 5.55 multiplied by 10 to the power 6 millimeter to the power 4. Okay? Now look, in order to find a Q, okay, we need to find A1 multiplied by Y1 bar plus 2A2 Y2 bar. We have 2 of A2 and 1 of A1. Do you get that? Now, what are Y bar? Again, similar to the centroid idea, we'll go from the center of this all the way to the location of the cut, which is the where we want to calculate the shear stress. Now, this is definitely 25. How about this one, ya shabab? كم الدistance هذا?
44.
44, which is 50 minus 6, not a 12, not a 3. This distance is 12, half of it is 6. Okay, so if we substitute this, we will get 76 multiplied by 12. هذا يا شباب الآن 76. ليه؟ This one is a 12, this one is a 12. It's part of the blue one. We're talking about the green. Multiplied by Y bar, which is 44. Plus 2 multiplied by 50, the height, multiplied by the thickness, which is 12, multiplied by the centroid, which is 25, and you get 70.128 multiplied by 10 to the power 3 millimeter cube. Remember, it's a cube. Cube, not to the power 4. Why? You are multiplying area, which is millimeter square, multiplied by one dimension. Yes, you have a question, yeah, Mohammed?
Yes, would it be easy if I turn everything to meter from the start?
Yeah, it's up to
It
you.
should be, because we will multiply it by kilonewton.
Just make sure that you do everything right, okay?
Okay, thank you.
Okay. Now, let's move on. So, the question is, if I have the cross-section like this, then I am definitely cutting this and this, which is 12 and 12. So, the equation will be B will be 12 plus 12, which is 24 millimeters. So tau maximum, which is right here at this cross-section, is going to be VQ over IB, which is equal to 40 kilonewtons. So you can multiply to the power 3. And then you will have Q, which is 70.128 multiplied by 10 to the power minus 6 in meter, divided by 5.55 multiplied by 10 to the power minus 6. This is the moment of inertia, multiplied by 24, 10 to the power minus 3. What is the result? It's going to be 21.05 megapascal. Point A is located in a very critical place. You can look at it this way. And point A is right there. Now, the thing that most of the students may not feel that they want to believe. And by the way, some of you will spend your entire life without believing it, or being confident about it, is that you can use this one alone, and point A belongs to it. So if you take it, you draw it like this, وتقول بأنه point A هذا هي. أو إذا أنت إنسان يحب التعقيد، بالإمكان إنك تأخذ الجزء الأسفل الجزء السفلي. And then you say, I'm gonna do all the calculation for this, and point A is right there. Interesting. Do you think you will get the same answer?
Yes.
Yes, absolutely. If you don't get the same answer, then all of the mathematics and whatever we do is garbage. It has to be right. No doubt about it. Yes, this one is easy. This is not difficult. It's more work. Many students come and ask me, really? And I told them, listen, you have to do this once in your lifetime. Just go home. We are going to solve this for the simple solution, and go and do the lengthy one. Just one. Once in your lifetime. And you will feel so happy when you see it with your eyes that actually it is true. They are the same. Now, so let's get to work. We are going to use the black region. Okay. Now, tau A will be equals to VQ over IT or IB. Now, I, we know it. صح ولا لا? V, we also know it. It's 40. باقي لنا شغلتين نحددهم. Q and B. خلونا نبدأ بالبي. وش تتوقعون البي مفروض تكون؟ هذا كل هذا أو هذا مع هذا؟
لا كله 100 200.
القلوب مكان القلوب
بيكون كامل 100 سالته.
دكتور المو كامل اصلا مكان النقطه تحت شوي. لو ترجع للسلايد اللي قبلها اشوف انها تحت شوي.
احنا اخذنا الجزء العلوي فالمفروض يكون فوق.
لا احنا اخذناها في المستطيل اللي فوق يكون كامل أجل.
في كل حالة تفرق، اللي فوق كامل واللي تحت بس الجزئين.
صح.
Okay. Well, listen to me carefully, يا شباب. Oh, you can calculate it with 100 and you can calculate it with 12 and 12. But the truth is, the right answer is to take 12 and 12, not 100. Now, why? Of course, the answer is not because we are up, not down. Actually, يا شباب, it makes more sense إنه البي في القطعة اللي في اللون الأزرق، هل في خلاف على أنها هي 12 and 12؟ ما في خلاف، صح؟ ما أتوقع أن في واحد يقول لي لو سوينا أناليسز للجيومتري هذه بأنه البي مفروض تكون 100. Anybody think so? I don't think. خلاص بعد واضح في 12 and 12. So think about it this way. How comes that B is 12 and 12 في الجزء السفلي و100 في الجزء العلوي ونقول لك إنه الكالكوليشن تطلع the same؟ أنت طبعاً بتقول إيه because the Q is different. B is not. No. B is the knife. You remember the knife story? You should feel the B the same way in both. Otherwise, you will get different answer. That's number one. This is just an argument. Number two is the fact that the story, the real story here, إنه الفرق في البي إن هي في الأسفل. هي في أسفل المعادلة في الدينومينيتور. إذا البي كانت 100 أنت راح تقسم كل المعادلة على 100 فالتاو will go down. If you take B as the 12 شو الفرق ما بين ال 12 وال 100 كثير صحيح؟ tau will go up. طبعا أنت تقول أوكي يعني وش الجديد؟ احنا في النهاية ما نهتم بالأرقام هل هي كبيرة ولا صغيرة، احنا نهتم بالحقيقة. Well, the truth is this. If you plot the shear stress distribution, the sudden change in B will be reflected in the distribution like this. So I'm gonna do it this way. Look, the shear stress will go like this, and all of a sudden will go like that. Now let me zoom in, okay? If I zoom in, okay, at around this point, you will see that this is like this and like this. Now the question, do you want to take... نعم.
عند النقطة هذه اللي تغيرت فيها الزبدة اللي صار فيها اللفة هذه، مو نروح على اليمين زيادة يعني كستريت لاين؟
Yeah.
بعدين نسوي
You will.
في جنب يعني.
Yeah. Sure. It's I may not have plotted this in precisely like this, whatever. But what I'm trying to represent to you is this fact. You are at the edge. إما إنك تقول أنا عند النقطة هذه والقيمة هذه مثلا 100، أو إنك تقول لا أنا عند النقطة هذه تحت شوي فأنا في الحقيقة القيمة 150. It's a very tricky part، صح ولا لا؟ So you are in a position يمكن 100 micron or even 1 micron in height might be 100. Below 1 micron, it might be 200. And in an engineering sense, we would rather intentionally go for the 200, not the 100. The reasoning is very simple. If I go a little bit up, 1 micron, I will be in the 100 region, and I will have tau divided by 100. If I am little down by 1 micron, I am at the region where thickness is 12, and I will divide by, not to 12, actually by 24. So there you go. That's the difference. Now, of course, we are engineers, and we are always afraid that we forget a large value that may put our design at risk. And hence, we are going to use the 24, 12, and 12. So to summarize, okay, the answer would be like this. B will be 12 plus 12, which is 24. And tau A will be equal to 40 multiplied by 10 to the power 3. And then 50. Oh, I forgot the Q. The Q, ya shabab, in order to find it, this is the center. This is the area that we are going to consider for Q. Now, the distance from here to there is 50. صح? So, what we are going to do, we need this area. This area, Q, is equal to 100 multiplied by 12. And then the centroid from here to there is 44. So I need to multiply by 44. And what would I get? I will get 52.8 multiplied by 10 to the power 3 millimeter cube. So this is 52.8 multiplied by 10 to the power 3. And then I divide this by the moment of inertia, which didn't change. And then multiply it by 24. And how much would I get? A stress of 15.85 megapascal. Understood, ya shabab? Yes.
For the B, why 24 not 12? Like for because point A only in the
point A. شوف shear stress هذا ولما تيجوا تعمل bending للبيم ما في هذا يصير له shear وهذا ما يصير له. point A is at a level. احنا ايش قلنا؟ عشان كذا اقول لك مثال السكين او المنشار مهم جدا. You are not dealing with the situation. تقول لا 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 انا بجيب السكين وبقص هنا بس. No. The cross section is one piece. When you apply the shear cut here. cut here. ما تقدر تقول للشير لا بس تعال هنا. You can't. The entire beam will bend, and that bending will cause a shear force going inside and outside, and you cannot control it إلا إذا سويت حاجة واحدة إنك تجي وتقول لا أنا بغير البيم طبعا هذا راح يغير المسألة كلها. فاهم؟ تقول البيم شكله كذا. هنا بوينت عفوا أنا كان قصدي كذا. هذا an open cross section, not closed. Do you get my point?
yes.
Which is totally different thing.
Okay.
All right, ya shabab, that's it. That's the end of the lecture. Thank you so much. See you next class.